Okay, thanks, Stephen, for inviting me. All right, so as Stephen said, I'm Goldberg. I'm from the University of Waterloo. I'm the Canada Research Chair in Privacy Enhancing Technologies and part of the CRISP, Cryptography, Security, and Privacy group at the University of Waterloo. And just quick plug, if any of you are graduating PhD students looking for a faculty position, we have openings in computer security and privacy enhancing technologies this year. All right, so this is joint work with my grad student Chelsea Comlow and Nick Mathewson from the Tor project. Okay, so we're going to talk about private web browsing. And when most people think about private web browsing, they think of incognito mode or something like that. So this is Chrome's version of private browsing called incognito mode, and this is Firefox's version called private browsing. But people have a lot of wrong impressions about what these private browsing modes do for you. So the Firefox version has this link right here, common myths about private browsing. So is it really private? That link itself, the first thing on it, myth 1, private browsing makes you anonymous on the internet. So that is false. Hopefully, most of you know what private browsing does for you. It basically just doesn't save any state locally on your computer, so that someone else who uses your computer can't tell what you've been visiting. But it does nothing to protect your privacy against a network observer, like an ISP or a telco or a government or something like that, or the web server itself. Okay? But this is a common misapprehension. So there was this interesting paper from last year that did a user study of what people believed private browsing mode did. And the misconceptions are kind of fundamentally ingrained. So here's a clip from that paper. This overestimation reaches far, Eric Schmidt, former CEO of Google, once stated. If you're concerned for whatever reason you do not wish to be tracked by federal and state authorities, my strong recommendation is to use incognito mode. And that's what people do, right? So, that is not correct, right? Many of you are making faces. The camera can't see your faces. Turn around for a reaction shot. But yeah, you are making the correct face, which is this is totally wrong, all right? So, what if we wanted to do private browsing for real? We want to actually protect our browsing habits and what sites we visit from network observers or from the website itself. So it will surprise no one if you know me that I'm going to say that the most popular solution to this is Tor. Okay? We'll talk more about Tor in a bit, in case you don't already know what it is. But, so the way most people use Tor is to use the Tor browser. This is a picture of the Tor browser. The Tor browser is just a modified version of Firefox, and it's modified so that all your network traffic coming from the browser goes through Tor. Okay? And it also closes other holes like certain browser fingerprinting attacks and other things that it has to do in order to better protect your privacy. Okay, so this is Tor browser, and like I said, this is the way that most Tor users use Tor, but there's some interesting new developments coming. So this is talking about the Brave browser, which isn't super popular. So like 2 million people a day use Tor today, mostly, as I said, using Tor browser. Brave has a user base of about the same size, 1 million or so. And Brave has experimentally made its private browsing mode optionally actually use Tor. Okay, so its private browsing mode is actually private if you turn that on. Okay, and it's currently in an experimental phase, but if they turn it on, suddenly there are going to be a bunch more users of the Tor network. Even grander scale, Firefox has announced that they're looking into having what they call super private browsing mode, right? SPB, super private browsing mode, which will use Tor. Okay? Firefox has a user base of about 100 million users. So if Firefox turns this on, suddenly there are 100 million users dumped on the Tor network. Okay? So, some of you are expressing concern. You are correct, and we will see why. All right? So, the point is that in the possibly not too distant future, the number of people trying to use Tor may suddenly increase. Okay? So keep that in mind. All right, so let's talk a bit about how Tor works. Who here knows how Tor works? Who could give me the next slide? Okay, so why don't you present? No, I'll do it. All right, so to fill in the people who don't know how Tor works well enough to present it themselves, let's just go through it quickly. So, the root of trust of Tor is the directory authorities. There are 9 of them, pictured here. Not really. They're represented here. Does anyone recognize this? Who these people are? It's the Supreme Court of Canada. I would not expect you to recognize. Fine, so this is the Supreme Court of Canada. I'm not saying that the 9 Tor directory authorities are operated by the 9 justices of the Supreme Court of Canada. That would be weird. But I will represent the authorities by these justices. Actually, I'll just represent them by this little icon of like stacked castles there. So it's this distributed authority. Okay? And generally, any action they do has to be signed by a majority of them. So 5 out of 9. Okay? So all the root of trust in Tor eventually is in these 9 authorities. Okay, so these are the authorities. Then we have the onion routers, also called relays or nodes. So I'm going to represent onion routers by onions. There are about 6,500 of these onion routers right now, and I'm going to represent the number 6,500 by the number 5. Okay? Otherwise the screen will get way too busy. Okay, now what happens is whenever one of these onion routers comes online, and every hour it stays online, it sends to the authorities this little document called a descriptor. Okay, and this descriptor describes the onion router, right? And it has things like its public keys and its IP address and port, and something called the exit policy, which we'll talk about a little later, and a few other things. Okay, it's not that big. It's a couple kilobytes right now. So each node is sending a couple kilobytes to the directory authorities every hour. So you have a couple, and then another one, and another 2. Then at the top of the hour, at whatever o'clock, the directory authorities all run a consensus protocol, right? It's not as fancy as the consensus protocols you might be used to. It's only kind of correct, but it's been running for a decade now, so, or more, decade and a half now, 15 years now. So it kind of works. And what happens is, in this consensus protocol, the 9 directory authorities end up agreeing on what descriptors they've seen from what people. Okay? Or from what relays. And then they all come to an agreement, okay, at least half of us have seen these ones. Does everyone agree on that? Yes. And then what they do is they create the consensus. So the Tor Network Consensus is a document that has, at the top, it just has a small number of like global network parameters, things like the current overall health and the size and things like this. But most of the consensus document is just the 6,500 descriptors, one after the other. And they're all, this purple seal down here is meant to indicate that it's digitally signed by at least half of the authorities. Okay, typically all of them, of course. Okay, so we have this consensus, which right now, as I said, is like 6,500 entries of about 2 kilobytes each, right? So that's like tens of megabytes, a little over 10 megabytes. If I did that right, did I do that right? Probably 10 to 20 megabytes. And it sends it to every relay. So every relay gets this tens of megabytes consensus every hour. Then what happens? So now let's look at the client. So this is the logo for the Onion browser, the Tor browser. So this is a client. The client starts, when it first comes online, it starts by downloading this consensus. So it connects to just any relay and downloads the consensus. Now, that's not a security problem because the consensus is still signed by the authorities. Okay? So the client can get it really from anywhere it wants. It can check that it's valid, that its timestamp is correct, it's the up-to-date consensus. The public keys for the authorities are, of course, baked into the client software. But you may ask, how did the client find this person in order to download from it? So originally what happened is when a client first came online, it always downloaded the consensus directly from the directory authorities. This sent a lot of network traffic to the directory authorities. This was not happy. So what they've done since is the client, in addition to having the public keys for the directory authorities, it also has a list of Tor relays that have been consistently up, that are stable, that are likely to be online. And so it will try some of those first. If all of those are offline, it'll go to the directory authority. But hopefully it doesn't have to. Okay? Hopefully it can find one of these nodes that are online. And it downloads this hour's consensus. Okay? Every client, of which there are, like I said, 2 million a day, does this every hour. So every client is downloading the consensus every hour. Okay? Now, originally that was literally true. More recently, because, as you might start doing the math, that's getting a little ridiculous, Tor has implemented a feature called consensus diffs. So it only downloads the parts that have changed, which is still, there's non-trivial churn on the network. It's not that small, the diffs, but it's smaller than the whole thing. Okay, so every client is downloading every consensus every hour. So keep that in mind for a bit. Now, what does the client do with the consensus? In Tor, in order to use the network, you need to construct what's called a circuit. So a Tor circuit is just a path through some number, usually 3, of the relays. So how does this work? So you have a client here, and the client is going to pick the relays for its path. Now how does it pick them? It turns out it used to be just uniformly randomly, but that doesn't work because different relays have different capacities. Some are on high bandwidth links, some are on low bandwidth links, and you don't want to spread the load equally across them. You more or less want to spread the load proportionally to their bandwidth. Right? So that's what Tor does. So nodes' bandwidths are measured, and clients will pick nodes proportionally with probabilities proportional to their bandwidths. Okay, that will be important in a bit. The other difference is that the first node is special. The first node that the client connects to knows the client's IP address. And so it is in a special position that it can point at the client and say, hey, that's a Tor user over there, right? So you often don't, you really don't want to pick a first node that might be adversarial. Right? You really don't want to pick any node that might be adversarial, but the first one's particularly bad if you do. So what Tor does, it has this concept of a guard. So a guard is an entry node that the client picks and then holds on to. So rather than picking a different entry node for every circuit, a client picks a guard and will use that guard for months at a time, like 9 months. Okay? So the client has a guard and picks the other two nodes from the consensus. So let's say the client is going to use these three highlighted nodes. So what happens is the client connects to its guard, and it does a Diffie-Hellman style handshake. We won't go into the details of the math, but we'll go a little further into it later on in the talk, and makes a secure channel between itself and its guard. Okay, so the bar indicates a secure encrypted channel. Over that channel, the client asks the first node, hey, forward this Diffie-Hellman handshake packet to that router over there, this one. And then it replies with its part of the Diffie-Hellman handshake, and now there's a green secure channel between the client and the second relay. Note the first relay can see the packets going on the green channel, but can't read them. They're encrypted to a key it doesn't have. So all it can do is shuffle the ciphertext back and forth. Okay? And similarly, over the green channel, the client now tells the second relay, hey, please send this Diffie-Hellman handshake to this third relay over here. That replies with its own, thus setting up the blue channel. So this is the circuit. Okay? Now, in order to use the circuit, say the client actually wants to talk to this web server over here. The client sets up what's called a stream. So once you have an established circuit, over this blue channel, the client can ask this third node, hey, please connect me to this server's port 443 or something. And that's what this black data is denoting here. Okay? And one circuit can serve multiple streams. So if the client wants to connect to a different server over the same circuit, it just tells the exit node over here, also go to this other site as well. And it can multiplex different streams over the same circuit. Okay, so what happens if Firefox dumps, let's say, 10 times the current number of Tor users on the network? Okay? Well, every Tor user has to download the consensus every hour. But in order to support 10 times as many Tor users, we're going to need 10 times as many relays. Okay, so the consensus will be 10 times bigger. So 10 times as many users are downloading a 10 times larger document every hour. Okay? That should start frightening. Right, because already this document is tens of megabytes. If that document were suddenly hundreds of megabytes, and we had to send it to 100 million users an hour, someone will be sad. Okay, so the goal, do not require every client to learn about every relay every hour. Now, there are some kind of obvious things you might try in order to achieve this goal, but the most obvious ones don't work. And I'll give a couple of examples. So the first obvious thing you might try is, instead of sending the list of every relay to every client every hour, you just send a subset. Okay? So you make the list shorter. So every client learns about a subset of the relays. So this opens up to what's called an epistemic attack, unfortunately. So an epistemic attack is when the adversary knows which relays you know about and which relays you don't know about. Okay? So let's say the adversary knows that this client knows about these relays but not these relays. Okay? Then any circuit that goes through relays in the gray zone here could not have come from this client. And conversely, any circuit that only goes through these relays is much more likely to have come from this client. Okay? And this, it violates the privacy that Tor wants to provide. Okay, so that solution is no good. Another possible approach is subject to a different attack. So let's say we have this client again connecting to this guard, but let's say now instead of having the client know about all the relays, the guard each node picks the next node. Okay? So this is a technique that was used in crowds in the 90s, and basically every node just picks the next node on its own. So the problem is, what if this node is in fact malicious? It's not an onion, it's pretending to be an onion, but it's really, I don't know, hot pepper or something, okay? Then what's it gonna do? If it's being malicious, it can just pick at random its buddies, right, who are collaborating and malicious. And so this one maliciously picks this collaborating hot pepper that picks that last hot pepper, okay? And it should be intuitive, if you think about it for a minute, that if a client circuit consists only of malicious and collaborating relays, then the client's privacy is completely lost, right? Because when the client says to this relay, okay, well, go to this website, this relay knows what website you went to, and it can, since all these relays are collaborating and can compare notes, this relay knows who the client is. And so the client's web activities are exposed. Okay, so this is called a route capture attack, and we want to avoid that as well. Okay. So, our proposal is called Walking Onions. Walking Onion is the name of an actual onion. This is like a food, the onion, right? It's a kind of onion that it has this weird feature where the onion bulbs grow at the top of the stalk instead of underground, and what happens is they get top heavy and they topple over, and that's where they germinate next season. And so over time, the plant kind of moves across the field like that. Okay? So that's the actual name of a plant. You can eat it. I'm sure it's fine. I have not eaten. Whatever. Okay, side story. Back at the very beginning of onion routing, like in the 90s when Paul Syverson and those people were first presenting onion routing, they held an onion dinner in Berkeley that it was like an onion-themed potluck. So, yeah, so I went to that. All right. I don't think there were walking onions there, though. All right, so Nick Mathewson made the first version of this proposal with a lot of open questions in it. So in this work, we build on that proposal, we address the open questions, and go further and make some better things. And he, as I said before, is a collaborator on this work as well. Okay, so here's the idea. The client has a guard. Fine. So the client has the secure connection to the guard. Now the idea is that when the client wants to extend this circuit to a second hop, the guard is going to pick the next hop. But you should just say, wait, didn't you just say that's bad? So the trick is that this is going to be what's called oblivious path selection. So the client is the one that determines which next, which relay will be the next hop. The client doesn't know the list of all relays, but as we'll see in a minute, what's going to happen is the guard is going to take the client's request, use it to choose a next guard, and then prove to the client that it did it correctly. Okay? So this is oblivious path selection because the client was able to choose the next hop without knowing who that hop is going to be. Okay, and then after this channel is established, the client can verify that the relay it's now talking to at the other end of the green channel is in fact the one that was chosen by the client's request. Okay, we'll see more details in a few minutes. Okay, so to see how this works, we need a couple of new data structures. So we have the current consensus, remember, is made up of this small network directory status information, which is not very big, and then one descriptor for each of the currently 6,500, but maybe in the future much more, relays. Okay? So, the first thing we have to talk about is the separable network index proof, or SNP. So what is a SNP? The SNP is this green document here. What it consists of is one of these descriptors, it's a relay descriptor, plus this index range. What is this index range? It's a range of, say, 32-bit integers. And the idea is that the size of this range is proportional to the probability you want that relay picked. So higher bandwidth relays will have a larger range, and smaller bandwidth relays will have a shorter range. Okay? Fine. And the SNP is itself authenticated by the authorities with a digital signature. We have a few different ways to do this. One way is with a Merkle tree, one way is with individual digital signatures. We have a couple options in the paper. Okay, so this is a SNP. So we'll symbolize the SNP by the green little folder with the seal on it, because each SNP is individually authenticated. Okay, so in the current consensus, each of the descriptors turns into a SNP. Then we have the efficient network directory with individually verifiable entries, or endive. And the endive is just all of the SNPs put together. Signed, technically it doesn't have to be signed because every element in it is signed, and you can tell there are none missing because of the index ranges. But it saves a step if you just also sign the endive. It saves the work of verifying every signature every hour that you receive. So you may as well sign the endive. Okay, and then the new consensus is in fact nothing but this network status information signed. Okay, so it's tiny. All right, so we have two flavors of walking onions. The first one we'll talk about is telescoping walking onions. So here's how it works. First, every hour the client still downloads the consensus, but the consensus is now just this tiny, tiny document. Okay? So no big deal. More importantly, it's independent of the number of relays in the network, right? So the amount of data each client is downloading is now constant rather than order n. Okay? All right, so each client still downloads the consensus, but now the consensus is tiny every hour. Okay, so let's go into a little more depth into how exactly these circuits are constructed. So what the client does is it sends a Diffie-Hellman key to relay 1, the first relay in its path, which will be its guard. So I symbolize that with key 1. And the relay replies with its green key 1. And now there's a secure connection. Okay, so that's just normal Diffie-Hellman. Well, it's not totally normal Diffie-Hellman because it's a one-way authenticated Diffie-Hellman, right? So normal Diffie-Hellman doesn't have any authentication built into it, and you don't want to use a a strongly authenticated bidirectional Diffie-Hellman because you don't want the client to be strongly authenticated because it's an anonymity network. So Tor uses this protocol called NTOR, which is a one-way authenticated Diffie-Hellman. So the client learns the identity of the server, but the server doesn't learn the identity of the client. Right. So anyway, that's what this bar means. Now, over this secure connection, the client will send its Diffie-Hellman to relay 2, but it doesn't know relay 2. It doesn't even know the list of all relays. It knows no relay except for its guard at this time. So all it does is it sends this random 32-bit number. Sends the random number R2 along with this key. Okay? Now, what this relay does is it looks in the endive. And some snip will contain this number R2 in its index range. Okay? So the index range partitions all 32-bit numbers. 32-bit is, of course, arbitrary. If you want more resolution, make it 64, whatever. 32 is probably fine. Right? So it picks a random 32-bit number. This relay finds the snip that contains that number in its range. There will be exactly one of them. And then the guard then uses that relay as the second relay and forwards the client's key along to that relay. And importantly, in the NTOR protocol I just mentioned, this one-way authenticated Diffie-Hellman, the client doesn't need to know who the person is it's talking to until the end of the protocol. Okay? So the first message is independent of who it's talking to. So it can send this to anybody. And so it'll get sent here to the second node. This node will reply with its Diffie-Hellman stuff. And then the guard will send along the reply, but also the snip to prove that this was the correct guard to go to and it's not a collaborating hot pepper. Right? So the client now gets back this key from relay 2 and the snip proving that relay 2 was correctly chosen based on the R2 from the client, that the client got. Okay? So now there's a green channel. And then third hop works the same way. The client sends its Diffie-Hellman parameter 3 and R3. Now, the guard can't even read this because this is in the green channel. But the guard just forwards it along, right? It's encrypted. Now, this node can read it and does the same thing. It takes R3, it looks in the endive, finds the snip that contains R3 in its index range, and uses that as the next hop. And say it's that one, and it sends along the client's key 3, gets back the server's key, and then sends back the server's key 3 and the proof in the form of the snip that this third relay was chosen correctly. The guard, of course, can't read this because it's encrypted in the green channel, so it just forwards it along, and now the blue channel is set up, and there you go. So there's the circuit. Okay? The client at no time learned all the relays in the network. The client only learned the snips for the relays it actually used. Okay. So one downside of this method, which is a downside in current Tor as well, this isn't a new downside that Walking Onions brought about, is that there were 3 round trips from the client, right? 1, 2, 3. And if the client is on a slow link, a mobile link, something like that, and there are like apparently about 1 million mobile Tor users now and growing, that can take a while, right? So the latency to set up a circuit will be limited if the client's link is slow, because there are 3 round trips over it. Okay, so we have another protocol called SinglePass Walking Onions. It's a little bit trickier, but as you might guess from the name, the idea is to set up a circuit with a single message that goes out and comes back. Okay? And proposals for this have been done before, but previous proposals had a forward secrecy problem. Okay, that we address in a way I'll show you in a bit. Okay, so what happens here? So the client now sends a public key, the Diffie-Hellman for its encryption, right, normally, but also another public key which will be used for Diffie-Hellman to help choose the next hop. And this is just a time to live field. This says how many hops more to go. So in this case it's 2. Okay, so what does this node do? It does the Diffie-Hellman, so with its key in, the client's key in gets the encryption key K that it now shares with the client. It does a Diffie-Hellman between this blue key and a part of its green key, and it puts that into a VRF, a verifiable random function, to get a random number R out, okay? And that R is going to be used to pick the next hop in the same way that we saw before. So this node, once it computes R, will find the SNP that contains R in its range, and that's the next person. That's the next relay. So why are these primes here? We don't want to just forward on the same keys we had here to the next hop, because a network observer could then see, oh, well, this message corresponds to this message. If there are a bunch of clients trying to extend circuits at the same time, you don't want to be able to trivially look at the network and say, that one corresponds to that one, right? So what we do is a trick from Sphinx, which is a paper from George Dinezis and myself 10 years ago now. Oh, that's crazy. Yeah, 2009. And so this trick allows you to take a Diffie-Hellman style key and re-randomize it in a way that only the people who involved in the Diffie-Hellman can figure out what the next value is. Okay? So these are re-randomized versions of the original key. And the 2 has turned into a 1, obviously. It's a countdown timer, right? Okay? This node does the same thing. It computes its key by doing the Diffie-Hellman on the yellow, and it does the Diffie-Hellman on the blue to get the value that's fed into the verifiable random function, gets R prime out, uses R prime to look up the SNP that contains R prime in its range. Say it's that one, and it read lines the 2 keys, sends them on, countdown timer of 0. 0 means you're the last node. Okay, so now this node just does its normal, it ignores this key because it doesn't need to choose a next hop at all. And it just does the normal Diffie-Hellman with that key, sends back its Diffie-Hellman parameter, green key 3. Okay, now what this one does is it sends back its Diffie-Hellman parameter, green key 2. That will establish a shared secret between itself and the client, K prime. Using K prime, the square brackets denote encryption. So it encrypts the SNP that proves that the last hop was chosen correctly, along with the value of R prime that was output, including, because it's a verifiable random function, the whole point is whoever produced the output of that random function can also produce a proof that the output was correct. And so that's bundled in here as well. And whatever it got from the previous hop, in this case it was just key 3. And then this hop does the same. It gives its green, and then all of this encrypted with the key it shares with the client, which is the SNP for the next node, the R for the next node, and everything it got from the previous node. All encrypted to key 3, except for that. And then once the client receives that, it can, layer by layer, work out the shared secrets it has with each of the relays and be convinced that the circuit was chosen correctly, right? It is important that note that the client's message uniquely will determine the path. There is no way for the relay to change its mind, right? Like if it wants to route you to a friend of his, there's no way for the relay to change something in the computation, that it can like try different things until the output is the one it wants.
That's because it's a fixed key for the VRF.
That's because the VRF uses what's called a semi-ephemeral key that changes. It can change like once an hour or once a day or something, but it has to be in the SNP already.
Okay.
Exactly. Good observation. Okay, and now the circuit is set up, and that was done with a single pass. Okay, so one message went out to the end, and one message came back. All right, so that's single pass walking onions. Okay, so the original proposal for walking onions only had some of what I've shown you, and it left some big open questions, including how to handle path constraints. So it turns out not every path through Tor is a desirable path. So there are a couple of different reasons. One is you don't want multiple nodes on the path to be part of the same network, for example, right? You also have issues with exits. So not every relay is willing to be an exit node at all, right? And this is because if you're not familiar with Tor, the exit node is the one that connects to the actual server. And so its IP address is the one that ends up in the server logs. So if someone is doing something untoward using Tor, it looks like it's the exit node doing it, right? And then people complain at the exit node, and sometimes exit node operators don't want to deal with that. Okay? I am an exit node operator. It is almost always auto-generated spam bots that the servers run to complain at you if someone tries to connect to their network. So I don't care about replying that. I always will reply once to the spam bot, but if it usually bounces because people don't configure their spam bots properly. So whatever. Anyway, so not every node is willing to be an exit node at all, and even exit nodes can choose what ports and even IP addresses, but mostly ports, they are or are not willing to send traffic to. Okay? All right, so let's say this node wasn't willing to send traffic to this server either because it's not an exit at all, or it doesn't like that particular port you're trying to send to, or that particular server. Okay? So what can you do? So there are kind of two cases. One case is where you're okay telling your constraint to the previous node. Okay? So examples of that are, I need the next hop to be an exit node, right? Or I need the next hop to not be in the same network as you or the previous hop, because this node knows the previous hop, right? So if you're okay telling the constraint to the previous node, we have a solution which is that for common path constraints, that, for example, I need the next node to be an exit node. Okay? What we do is we include multiple ranges in every SNP. So the main index range is just weighted by bandwidth, and that's the one you use to choose middle nodes. But there's a different index range, which is what you use to choose exit nodes. Okay? Because that is a very common constraint. And so we just hard code that constraint, as it were, into the SNPs. So when you want to use an exit node, you just say, and pick from this column over here. All right? If you don't want to tell your path constraint to the previous hop, like let's say you want to exit to some port, particular port, and you don't want the middle node to know what port you're trying to exit to because it has no business knowing about the contents of the traffic, right? So worst case, you can always discard the circuit and try again. And that's fine if the path constraint is commonly satisfied. So if you're trying to exit to port 443, but through some weird random happenstance, you got picked an exit node that didn't exit to port 443, there are some, then you just say, well, screw that, and try again. It's unlikely to happen in the first place. It's double square unlikely, I guess, to happen again. Okay? But if your path constraint is one you don't want to tell to the previous node and is not commonly satisfied, like you want to exit to a weird port that only a few satisfy, well, so you make your connection, you try to exit to that port, the exit node says, I don't exit to port 31337. But what it can do at the same time is use the same VRF trick to pick another node for you that will exit there. It doesn't make that connection, it just points it out to you. And in the error message that it sends back saying, I'm not going to do that, it says, but you might ask this person, along with a proof that that person was chosen deterministically from the client's messages, right? And not in a way that this exit node could have biased, right? And then the client can set up a circuit with that node, a totally other circuit with that node as the exit. Okay, so here are some graphs, because graphs are pretty. So what are we seeing here? So the purple line is idealized Tor. What do we mean by that? So it turns out Walking Onions makes kind of two independent improvements. One is all the stuff I showed you, but the other is that it turns out the descriptors are unnecessarily verbose. They use like English words as tags for things, and that takes up a lot of bytes that aren't actually needed, right? You can have a much more efficient descriptor data structure, okay, and serialization. So idealized Tor is Tor with those improvements, okay? So you take Tor and you make the better data structures, so you're not sending a bunch of bloat around, and that's what you get as the purple line, okay? Then we have SinglePass and telescoping Walking Onions with different choices of how the SNPs are authenticated. So this is with a Merkle tree and this is with a threshold signature, okay? And there are trade-offs between these two, as we'll see in a minute. So note that idealized Tor is already like 1 to 2 orders of magnitude better than current Tor, okay? So if we beat idealized Tor, we are like blowing the fins off regular Tor, right? What is that? I just made that up. I don't know what that was. Sharks are your friends. Okay. All right, and this vertical line is you are here. That's the number of relays currently in the network. Okay? So, this is on the relay side. How much traffic do relays experience? Just for, like, not for routing traffic around, just for setting up connections. Oh, good luck. Just for setting up connections, okay? And for maintaining, like, the state, the endives, all the meta stuff, okay? But not for the actual traffic itself. Okay, and what you can see here is that even at the current size, the threshold versions of Walking Onions, and this is a log scale, this is a log scale in fact, right? So lower is way better. Right, so the threshold versions of Walking Onions already beat idealized Tor, which is already an order of magnitude or more better than actual Tor. And the Merkle ones aren't as good now, but have a crossover point later. Okay? So if we get way more users and we need way more nodes, that might be something to look at from the relay side. From the client side, there's not really a crossover point, because for the whole point of this was to keep clients from downloading anything that's proportional in size to the number of relays. Okay? So the threshold version is in fact constant. This is completely independent of the number of relays. The Merkle version has this small thing which is logarithmic in the number of relays because there's a Merkle tree. Because that's how Merkle trees work. So there's, when the client is building a circuit, part of the proof that comes back is a Merkle path, which has length proportional to the logarithm of the number of relays. But it's still very small. And even at the current size, both versions beat the current Tor. Okay, so takeaways. If we want private browsing to be actually private and lots of people to use it, like way more people than currently use Tor, we're going to have to make Tor better. Okay? Walking Onions importantly removes the per relay bandwidth cost to clients. Also storage, it's not as big of a deal because clients generally have a lot of storage. Photos are big, phones have gigabytes of storage. But if the current consensus is 10 to 20 megabytes and the network gets 10 times bigger, we really don't want to be downloading and storing 100 megabytes all the time, right? But it's the bandwidth that's really the more pressing issue there, more than the storage. And Walking Onions offers the same security against attacks like the ones I talked about, epistemic and route capture attacks, as previous proposals, including the current design of Tor, without requiring a globally consistent network view. Okay, thank you very much.
Any questions?
Yeah.
So this is kind of open-ended, but I was wondering about the incentives for users. So what's best for users and what's best for the network?
Right.
So I can imagine that as a user, it's to my benefit both in terms of reliable service, quality of service, and perhaps anonymity to use larger relays. So have you observed anything around that, like users avoiding or kind of blacklisting smaller relays? And
so the network already takes that into account, and it already blacklists the slowest of relays. So any relay that is allowed to route traffic at all has to be at least this fast, right? And over the years, Tor has upped that bar. One issue is that if you up it too far, then you have excited volunteers that want to help out. There are people who saw Roger speak at CCC or something and are excited to help with the Tor network, and they put up a relay in their house and they can't do a lot of traffic. And you don't want to discourage those people from helping, but we have some other papers, in fact, that show that there are other useful services you can do also to help Tor scale, but that low bandwidth nodes can act as those servers and not to just relay traffic. So this is, again, area of active research that we hopefully will see that encourage more people to join the network from the relay side. Other questions? No? Okay, thank you very much.